This is going to be the last part of gear design procedure. So in the previous two modules or two parts, what you have seen, I'll just quickly narrate, and then we will go in this particular video lecture. Okay, in the first part of this gear, of course, we started with the classification, which video I have not done. So that was material of that is already put up on Google Classroom, and I have narrated through PowerPoint presentation only. And after that, part 1 video lecture, I have narrated about Levy's equation, and then in the subsequent part 2 design procedures we have seen. In addition, basically we have three type of what you say design modules in gear. One is a static load design, and dynamic load, and then wear load. Static we have seen, in which there are 5 different steps, sub steps of design, like assuming the material, and then minimum number of teeth on pinion, and then checking for the finding the module, and then checking for induced stress and all those percentage variation and all. So which I think by this time you have already gone through that video. So in the subsequent, what I'm going to narrate is that design procedure for dynamic loading. So again, dynamic loading and wear loading I am going to complete in this particular module only. Okay. So basically, that as I mentioned, 5 steps we have seen in previous. In this particular this thing, we start with the step number 6. So that is strength of gear tooth against dynamic load. So I told dynamic load. Actually, there is one more this thing called as Buckingham's equation. So that is what is being mentioned in the bracket. Okay, probably you may get surprised. Reason is this in a static load, this thing only Lewis equation, we have already taken in some sort of what you say the velocity factor in the last expression of Lewis. That velocity factor is basically in order to account for dynamic. Okay, probably you may. So that is just a quick thumb rule what that Lewis has narrated. After that, people have done a lot of this thing, what you say, sort of testing, and again they have come up with that. So in that context, Buckingham, that credit goes to Buckingham, who has given this dynamic. So I'll just read it out and then parallelly narrate. Okay, in a Lewis equation, velocity factor CV is considered to account the effect of dynamic loading. Okay, so basically the dynamic loads are due to following reasons. One is irregularities in tooth spacing. What do you mean by in irregularity? So the tooth spacing is there. Okay, so that tooth spacing, this particular whatever this distance is there, so this will not be uniform throughout that particular what you say gear diameter, because of what you say lacuna in the manufacturing or material defect or whatever it may be. Some that person who is manufacturing, his error, all those constitutes irregularities. And there is one more irregularity on the tooth profile. What do you mean by tooth profile? So this particular whatever that form is there, no, involute. So this is also that irregularity may also be there. So the tooth profile. And again, last one problem of dynamic this thing is deflection of tooth as a whole in loading. What do you mean by that? Deflection I told. So that if you consider a non-rigid body, a tooth is going to get deflected whenever it comes in contact with one particular pair. Okay, so because of all this that criteria, you notice that there is going to be sort of dynamic load coming into picture. Okay, a closer approximation to actual condition may be made by using equations based on practical tests as mentioned below. As I told, they have considered practical test, and then finally they have come across this particular relation. What is that? Dynamic load equal equal to that dynamic FD is a dynamic load equal to FT plus FI. FT already we know what is that FT. It is a steady load due to transmitted torque, or you can say tangential load. Then what is FI? FI is incremental load due to dynamic action. So in the subsequent slides I will just show how is that going to vary and all those. So please note down, FT is a tangential, FI is, it is a summation of FT plus FI, where FI is a incremental dynamic load. So that may be changing after every cycle of rotation of that particular gear. The incremental load, just observe here, depends upon both depends upon pitch line velocity, okay, the face width B, material of gears, the accuracy of cut, and tangential load FT. So please note down, there are a lot of parameters which will govern the incremental load Fi. So we need to take all these and then try to find out the incremental load F. Okay, after seeing that FD, again I am just narrating this. So for average conditions of mass of gears, the following equation applies. That means it is this expression is going to be applied for mass, that is for a large variety of gears it is going to be valid. So what is that? FD equal to FT plus Fi. Okay, FD equal to FT plus Fi, and the one condition is this FD should be less than or at least equal to Fs. What is this Fs? Fs is dynamic strength, or it is dynamic load, which is given in the expression 12.16 page 208 of this particular thing. So what is that? Sigma d is the static strength. Please note down, it is a static strength. B is the face width of the gear. Y is Lewis form factor multiplied by pi, and M is the module. So in case this particular is not been done, again this you are not going to validate, so you have to check that particular. So this FD, that is whatever the developed dynamic load, that has to be less than the dynamic strength. Okay, in case if this condition is not met, then what you have to do? You have to do the iteration which is mentioned in this particular bracket. I think it is same what you have done previously. If the condition FD is not less than, or in other words if FD is greater than Fs, then change factors with minimum iterations. Remember that minimum iterations means don't go on changing everything, just change one particular value which you can quickly do that, and then ultimately satisfy the condition. Either you change B is what? Face width. Suppose that B generally it is for spur gear, it is in the ratio of 9.5 m to 12.5 m. Suppose if you have taken that particular B value, I think it is K by M equal to that, K is that, and then again B equal to that particular 9.5 to 12.5 to M. Okay, ultimately. So if you have taken that particular between that range, you enhance that to, suppose if you have taken 10, you go for 11, 11.5, 12, and so forth. Further, if it is not been satisfied, that is if FD is again still greater than Fs, then again you have one more option like changing the material. Okay, material means what? That whatever gear or pinion design criteria you are doing, the material of that you can change. But again here also there is a limitation in the sense, if a material is already given in the problem, you can't have the liberty to change that. Then last option is left out, is go for higher module. Okay, so please note down, changing module, all the steps please keep it as a last priority. Last priority means suddenly you don't jump for changing the module, because what happens as a designer, you should be very much cautious. One is strength, that is safety, and second one is economy. I think economy plays a vital role in current situation. So because if you unnecessarily go for higher this thing module, again the cost of that gear, cost of that component, cost of that machine or whatever it is going to be designed, so it is going to be enormously, and affording again will be less. So in that context, unnecessarily don't go for, that is called as over design. So don't go for over designing of that. Okay, this FD, whatever that relation I told, it is given in the page number 207, equation 12.12. Okay, and again subsequently we know how to calculate ft in the previous. Already you have calculated fi. We will see fi is given by, I told in the previous slide, there are lot many parameters which govern the fi, like accuracy of the gear, face width, pitch line velocity, material of the gear, and all those kind of things. So which is been, of course ft is also going to govern that fi. So again, taking all this expression has been narrated, that is K3V inside the bracket capital C into B plus FT bracket complete divided by K3V plus root of C, that is capital C B plus FT, wherein K3 it is given actually, you have got in the data book, please refer, there is no separate expression for fi. It is given just below this expression in the data book. Just go through again. For that, K3 is a unit factor. What is that? For SI unit, one particular unit is there, that is 20.67. Do refer. For MKS there is one more value. Since we are referring only SI unit, you have to be very much cautious, so you have to take that particular K3, okay, that correspondingly. And C is the dynamic factor, so that is again given by one more expression, that is small e divided by K1 inside the bracket 1 upon E1 plus 1 upon E2. What is that E? E is the measured error, okay, that is the error in the profile, okay, in millimeter, and K1 is the form factor constant. Again, for 14.5 degree, 20 degree, stub tooth and all, you have different values in the data book. Do refer that. And E1 and E2, what they are? They are Young's moduli of pinion and gear respectively. That means E1 is for pinion Young's modulus and E2 is for gears Young's modulus. And if Young's modulus is given in the problem, you are lucky. Most of the time it will not be given. So a lot of challenge for you. It is available in the data book, not in the gear section, but separately in the beginning of that. While solving the problem, I will show. Or else what you can do, most of the time for both cast iron as well as for metallic steel, that carbon steel, that Young's modulus will be varying somewhere from 200 gigapascal to 210 gigapascal. You have the liberty to take 200, 201, 202, 3, 4, 5, any value for that matter, since it is an assumption. Okay, basically it's an assumption, but in the professional this thing career, what you can do, you can't do that. What you have to do, you have to get this particular Young's moduli from the supplier, or else ultimately you have to make that specific testing. I think you know tensile testing, how the Young's modulus is done. Basically it is a ratio of stress by strain. You have to give it to that particular specimen. The dumbbell specimen you have done in third semester material testing lab, no, like that you have to do the, give it to some labs and then get the value of E1 and E2. Okay, so and again E, you will be surprised. E, there are two. One is a probable error and another one is permissible error. What do you mean by probable and permissible? I will slowly narrate. Probable means you don't know the accuracy of gears or class of gears. That means you are not clear whether it is class 1, class 2, class 3. In that case you have to take a probable error. Probable means tentative, maybe. Okay, how we can take that? There are tables actually, that is 12.12 page 237 for probable error. Okay, so that you can take, or there is one more figure 12.4. From that particular figure you can refer. That figure 12.4 and 12.5 are on page number 9. In that 12.4 is I think if the class of gears is known, I think you can refer this. Sorry, 12.4, 12.5 are for known. I think just check that 12.4 is if the class of gear is known, and if it is not known, I think 12.5 figure you can refer either, or you can refer this table. And if you know that particular class of gears application and all, then that is the permissible error. Permissible means the error cannot be more than that. Like that you should select and then substitute in that expression and then find the value of C. That C has to be back substituted in this Fi expression. Or there is one more table number 12.12 page 236, where you can directly get the value of C. But again the problem is, if you know the data and if your whatever that value is there, if it happens to be within that range, you can go for that. Or else best what I suggest is you go for the finding the value of C and then substituting it into that particular what you say expression. Okay, so we will go next. So I think I told how that incremental load and then tangential load and then dynamic load. Okay, so this is one case wherein with respect to time along x-axis the load will be varying. Please note down, the load is on one side, that is it is on positive only. In all the time it is positive, but it is varying with respect to some mean value. So with respect to mean value, that is mean value means what? Ft is a constant. This is going to remain constant throughout that particular, what you say, that cycle of operation. Ft will be constant. With respect to that, Fi will vary. Vary means one particular cycle, I think you can see the jerks, no, that jerk will be at every increment, thud thud thud, something like that. While in the probably bicycle or two-wheeler or even in the car, you can notice that jerk is at a particular frequency of a time, not continuously, so that varies a sinusoidal manner. So that is the incremental. Okay, so please note down, in this is the dynamic total from where to where, from a zero line to the top, that amplitude of this particular cycle, that is Fd, which is given in this particular condition, that is Ft is greater than Fi. So Fi value, compare it to Ft, it is less in this case. Okay, in the subsequent slide where you can notice Ft is going to be less than Fi, that is also possible. So like this, see, and one more thing over here is this Fi, it is for some time it is a positive and another time it is also negative, it goes negative. You can notice some sort of negative impact will also be there. So here it is going to be very crucial. So of course Fi is greater than Ft in this case. I think probably you may ask why you are not considering this. So basically Fi is with respect to mean line, okay, from here to this particular crest. Okay, so that is how, so this value is going to be greater than this. So under that condition, so the designer should able to take it into proper this thing. And one more thing is E and F are teeth separation, that is the load comes and then they separate out, and suddenly that load will be changing from one particular form to another form. I think in part number 2 I told that design is going to be very much crucial. Through this figure you can just visualize that. Okay, then further after finding that what you say dynamic load, you have checked actually for dynamic strength, but again that dynamic strength, whatever that Fs is there, no, so that there we take sigma d. Sigma d is what? Static strength we take. We never take the dynamic strength there. So under that context, once again you have to refer this particular step and then verify for endurance limit. What is that? Fen. Please note on, it was Fs sigma d was there and module was also there, but here I think module is not there. So F sigma endurance, B is the face width, capital Y is point to Y, this has to be greater than Fd. This is given in the expression 12.13 page 203, and for sigma endurance you have to refer this particular table only. There are multiple tables which I will be telling, so you have to be very careful. You have to refer table 12.15 page 238. Okay, this is the condition. If this condition is not met, then what is the conclusion? Design will fail. What do you mean by design will fail? The gears are not safe for dynamic loading and they cannot able to give the particular function, and at any moment of time there may be lack of what you say functionality. Lack of functionality means suppose if you have designed that gear for power transmission, the gear tooth will fail and power transmission will not be there. So then again what you have to do as a designer, you should see to it that it should function properly. Then what you have to do, if this is the case, that is when F endurance is less than Fd, what had to be done? In such case, choose the material having higher endurance limit from the table. Okay, do not refer table 12.16. As I told, do not refer this. This table is for something else. 12.16 is for something else. 12.15 is for something else. Okay, of course I have not told here, that is if the material is given in the problem, then again I told you don't have the liberty, which I have not this thing. Okay, I think I have mentioned here. Okay, in case the material changing option is not there, that is if the material is already given in the problem, then choose a higher module until the condition is satisfied. Okay, it is as simple as that. Okay, and the next next subsequent step, I think it is quite simple. There is no complication. It is again, if this condition is not safe, met, go for higher module or change the material. Okay, changing the material again. If it is material is not given in the problem, you have the liberty. If material is already given, you don't have the liberty. And again, one more this thing is this you remember in your professional life. Generally, we just speak margin of safety. What is this margin of safety? It is as good as a factor of safety, similar to that. Okay, suppose this you please make it in your professional this thing design is, suppose if you enter into design arena, okay, design area, so then you, while doing the gear design, you do this. Okay, so that is, there are three condition, the thumb rule, that endurance limit for steady load. Okay, that is F endurance, whatever is F endurance is there, this value don't take it directly from that, so you take higher value, that is you take 1.25 times FD. Okay, endurance limit for pulsating load. So just see what is that: steady load, pulsating load, and then shock load. Okay, shock load is sudden, pulsating is, so it shuffles between positive type of loading, negative type of loading, as I showed in the previous, and steady load is a constant load, so it varies. F endurance, it is 1.25 times, 1.35 times, and 1.5 times. Okay, and margin of safety is this, and remember, margin of safety should be always greater than 1 as a thumb rule. So you have the equation numbers shuffled over in the data book, 12.13 B, C, and then D on page number 208. Okay, so just have a quick glance, and then eagerness why it is required and all that kind of stuff in a regular class we will debate in this, in case if you have any query. Then we will go to the next. So next slide is going to be the last slide. So that is a step number 8 for strength of gear against wear load. Okay, so this is going to be the last step. So that is very simple, and remember, I told actually in the beginning of the that I think slide part number 2, that design procedure, irrespective of your design criteria, all the time wear test has to be done for pinion only. Why pinion? Pinion, it is smaller in diameter, so RPM of pinion compared to RPM of gear will be more. Why it is more? Because it makes more number of revolutions in one particular time period, because it is a smaller, so quickly it will make one circle in that stipulated time, whereas the gear, it is a larger, for one particular stipulated time period it takes longer time to complete that one revolution. Under that condition, since the pinion makes more number of traverse or more number of revolutions, so what is that? More number of revolution means more number of frictions of per each surface of that tooth. More number of friction means more chances of wear, or in other words, I will give you the classical example. Suppose two of your friends, okay, one you and another one more person, you have the same body weight, same what you say shoes, that leg size. Okay, and again both are having same what you say style of walking, let us assume like that. Okay, now what you do, you purchase a shoe, a same brand shoe. Okay, Bata only, Bata shoe, same number, same model shoe you buy, and again every day you have to wear the shoe. Okay, wear the shoe, and assume that one person is residing in hostel, another person is residing in toll naka, another person is residing in toll naka. So you will be coming to the college, you will be coming to the college, you know, toll naka, you know. Okay, the person who is coming to the college from hostel, remember that every day you will come only one time in the morning, and then again afternoon lunch you will go to that person residing in toll naka will go to toll naka, and person residing in hostel he will go, and then again come back to the hostel, and evening go. Only 3 times they will use the shoes. Okay, let us assume whose shoes will be wearing much faster comparatively after 1 year or whatever it is. Try to assume shoes are used exclusively for college purpose only. Let us assume. You can notice that the more number of steps the person who is residing at toll nakas shoes will wear first, because more number of traverse. Similarly, pinion, it is having more number of traverse in one particular cycle, so it will wear first. Under that condition, wear test has to be done for pinion only. So there is no derivation. Again, this is also given by Buckingham only, Buckingham equation only. So that is d1 B Q into K. What is that? D1 is the diameter, pitch circle diameter of the pinion, B is the face width of that gear, Q is the ratio factor, okay, and K is the load stress factor. So that is given by D1 equal to M into Z1, because D equal to M by Z, so that this thing, so under that module equal to D by Z, or D equal to M into Z. So Z1 B Q K, this has to be greater than dynamic load, because wear is going to be very much predominant, so that resistance of that wear should be greater than the dynamic load, which is given in the expression 12.5a, page 208. Okay, for load stress factor you have to refer this table 12.16, depending upon the endurance strength. Remember that endurance strength of this wear is surface endurance. Surface endurance, the previous endurance what you have referred is core endurance. I will just try to narrate. I have drawn with the freehand this thing, a particular profile. Just see the darker one. So the outside, generally how that surface hardness is achieved. Surface hardness is achieved by induction or nitriding, cyaniding and all. So remember there, as the hardness goes on increasing, the brittleness of the material goes on increasing. So that is why what they do the case carburizing or surface hardening only. What do you mean by that? Only for wear you should have the more hardness, and for inside core you should have the soft material. Okay, so the core should be soft. Why it should be soft? It should be capable of taking what you say, a bending load for that matter, or tensile load for that matter. If everything is made uniformly hardened, then what happens? It will be fragile or brittle. It will be brittle and it cannot able to take up the jerk load or tensile load. It will break off, as you are aware. So that is why they do like this. For that context, the one which you have referred endurance is the core endurance in the previous step, that is dynamic load. Here it is a surface endurance. Under that context you have to refer table 12.16, page 239 only. And again, K is also given as a sigma endurance square into sine alpha divided by 1.4 inside the bracket 1 upon E1 plus 1 upon E2. This is also given. You can very well do that. For sigma endurance, if you can refer the same table, or else what you can do, generally BHN will be known. Okay, so through that BHN, again it is given, all are given one below the another. Just browse through your data book. 2.75 into BHN minus 70. So that BHN is again average BHN of gear and pinion. That means you have to add both divided by 2, multiplied by 2.75. In that 70 you have to deduct, and that you have to take. Please note down the units are Newton per millimeter square only. Oh, okay. Or as I mentioned, sigma endurance can be referred from table 12.15. That is what I told. To notate, considering core BHN equal to surface BHN. That means whatever BHN is there, or that again BHN is also referred in that particular table. You make an assumption and then take it directly. Okay, that is what is this thing. While solving the problem, we will go through once again. What I request you, listen my video with earphone preferably, and go through that data book. Just evaluate, think, and then come to the class. Okay, that next class whenever we meet. Okay, and again one more condition which I have mentioned last. If FW is less than FD, that is if this condition is not met, whatever is mentioned, then what you have to do? You have to equate FW equal to FD. What do you mean by equate? You replace FW, okay, by FD value. That whatever FD you have calculated in the previous step, you substitute that value here, that FD value, and try to find the value of K. Okay, so K you don't substitute. Suppose when is that? If this condition is there, that is FW is less than FD. So what you have to do? Substitute FW equal to FD. That is FD is previous whatever that dynamic this thing load you have found out, that you substitute, and then find the value of K, and that value of K you have to locate it from table 12.16, page 239, and you have to decide the material combination. Please go through that table, that material combination, pinion and then gear. They have given the combination. If it is cast iron, steel, or steel cast iron, something like, they have given the combination. You have to choose that combination by knowing the value of K. And please note down, the K will not be exactly same as what you estimate. Suppose the K value is less, what you have to do, you have to choose the higher value of K and then decide the combination. Okay, so with this, design procedure will be over. Please listen it repeatedly. And again, most of you are asking, when I just post it on the YouTube, you will not be able to access this video directly from the Google Classroom. You will receive separate email actually from YouTube. That link you have to enter. Please don't delete that link, because I have observed people delete and keep on asking, SS, give me the SS and all. SS will be given only one time. What you do, you make a folder in your email and then go on storing all those emails in that with whatever that class notes, video link or something. So you preserve. Whenever you want to have doubt or something, please listen repeatedly, because I have taken utmost care in making the video, and in the regular class it may not be possible for me. You listen, so that we will quickly browse through in the regular class and go for solving the problem. So with this I'll stop. Thank you.